Welcome to our discussion on special exceptions to the Aufbau Principle. Today's discussion is fairly brief. You've already learned how to draw electron configurations and orbital notations, so follow along and take some notes with me about some exceptions to what we've already learned. What you see in front of you here is an image of the fourth energy level, at least most of the fourth energy level, with a couple of notable exceptions there. And what we're going to say about this really quickly is that we need to understand, before we talk about exceptions to Aufbau Principle, the most stable possible electron configurations are in descending order this. Full sublevels are the most stable electron configurations. So if you're looking at what's in front of you, S2, D10, P6 are more stable than anything else. Second most stable would be half-full sublevels. Half-full sublevels such as S1. Really no other choice but half-full. Then D5, and then P3. Knowing that, everything else being less stable than those two configurations, it makes sense that copper would take on a D10 and that chromium would take on a D5, sacrificing one of the S sublevel electrons to take that half-full for chromium and completely full sublevel position for copper. So, having said that, let's look a little closer. Chromium, Aufbau predicts, is going to have the outermost sublevel electron configuration of 4s2, 3d4. Everything up to 3p6 is going to be argon's configuration, stable as all get out. It's the valence shell electron configuration that's going to be changed. 4s2 consists of full s sublevel and 4 electrons out of 10 in the d sublevel. This is not terribly stable, but the atom has a lower energy state. In other words, there's a way that the atom can arrange these electrons that is more stable or of less energy. So what happens is one of the s electrons occupies the d5 position, and you get the configuration 4s1, 3d5. And that is because the atom is more stable with half-full sublevels than with this partially full sublevel and a full sublevel. Okay, so it sacrifices a little bit of stability here to get a lot more stability in the D sublevel. So chromium is always going to end in 4s1, 3d5. Similarly, copper, Aufbau predicts, is going to end with 4s2, 3d9. And you should see that we have this unhappy configuration here of a D9, and you have this electron in the S sublevel that can be made half full by giving one electron to make the D sublevel completely full. So instead of full and unhappy, we have half full, completely full. This is a more stable configuration, or you can also say that the atom in this electron configuration carries less energy. So those are some exceptions we need you to know. Now there are many others on the periodic table. You may read about them on your own time, but you're not responsible for knowing them. These, for our assessments in this chapter, will need you to know them. The final thing I want to discuss for the Aufbau principle is the excited electrons. We talked a lot in this unit and saw some interesting things in our flame test lab. And we talked about electrons being excited. And we want you to understand, what does that mean with electron configuration. So let's say we have potassium atoms and we're going to excite some potassium atoms. We did that with potassium chloride. And what we're going to do is excite one electron. So here's my 4s1 electron. That's the most valence electron in potassium. Let's say that a piece of X-ray energy or some kind of energy collides with that S1 electron. That electron is able to go anywhere above that configuration. So it could go to 3D1, or it could go to 4P1, or it could go to 5S1, it could go to 6F1, it could go to 9D1. Notice how I'm putting ones all these. That's because there would only be one electron in that orbital. But it can go as high as is theoretically possible. If you give an electron enough energy, it can be completely ejected from the atom. But what we're talking about here is an excited electron that is going to fall back down to its ground state and eject an equivalent quantum of energy, and that energy's value would be equal to Planck's constant times frequency of whatever type of electromagnetic radiation was emitted as it fell. So an excited state configuration is essentially going to be one electron going to one particular energy level, sublevel, above its stable ground state. So frankly, that electron can go anywhere there's a theoretical position for. Okay? There's even orbitals called G, H, and I. So theoretically possible. But what we're inclined to show you is something along these lines, where no matter what, you will know you have potassium because you can simply count the electrons present and say, oh, I've got 19 electrons. 19 electrons, if this is a potassium atom, 19 electrons means it's potassium. So understand that an excited state configuration just consists of one electron above its ground state in some energy level. It will always be a 1 in the exponent because that'll be the one electron in that sublevel. I hope this video has helped you understand some interesting exceptions to the Aufbau principle. Again, if you have questions, please write them down as you watch the video. We would love to discuss it with you in class or in tutorials to make sure that the learning is clear. Any misconceptions you've got, we want to clear them up right away. But above all else, any discussion you can provoke in class can help other people. So we look forward to seeing you there, and have a wonderful day.